So we have our next presentation ready. This is Shyam Nambiar from Analog Devices, presenting a case for distributed intelligence throughout the signal chain, enabling practical wireless solutions. Thank you very much.
Right. Thanks, Derek. So good afternoon, everyone. Like Derek mentioned, I'll be talking about distributing some machine learning throughout the signal chain in order to enable more practical wireless system solutions. And instead of focusing everything to one baseband or FPGA, can you do better on a system level by distributing the machine learning load throughout the signal chain? So I'm an applications engineer. I work with the transceiver products group at ADI. Just brief bio. So today I'll just give you a high level what's happening in the market, industry type of thing about the current wireless landscape. What are the scalability challenges that we currently face in the industry? Talk about digital pre-distortion as a systems efficiency booster and the complexity that it entails by getting over a few overview slides first. Since we're talking about DPD, we also need to talk about power amplifiers and understand some of the problems that most system designers face when using digital pre-distortion, because the power amplifier is a high power RF device and imposes its own challenges. So we'll also talk about some PA and DPD co-design issues and investigate the state of the art. I'll try to derive some figure of merit by proposing a system spec for a 2T2R small cell system, and that's a 2x2 system, and provide some architectures that are prevalent in the industry right now and try to compare them. So jumping right in, small cells and massive MIMO are two of the ways that we can get towards what the future demands. So small cells attacks the current market requirement of coverage and capacity improvement, and it's a necessary step in getting us towards almost omnipotent spectrum everywhere and available RF. Same thing with massive MIMO, and massive MIMO here is anything more than 16 signal chains. And massive MIMO here typically means 64T, 64R systems, or even 128 by 128. And this is seen as a road to 5G, if you will, like a 4.5G kind of stepping stone towards 5G. So we're talking about these two things today mainly because I see them as two pillars of what's going to come up in the future. And what I want to get down to, the core question is, how do we scale? How do we scale what we have, the current ecosystem, into a small cell or a massive MIMO? So as always, size, weight, and power is a constant reminder to us that real systems have finite limitations, and therefore you have a cost constraint, which is determined by size, weight, and power, or SWAP. So this is a graph that keeps getting pushed out every year. The small cells the growth is promised forever, but never really takes off. But I think mobile experts will probably want to say this time it's for real. Even the massive MIMO growth that is shown here is also predicted, but we definitely see trends in the current market that are indicative of these types of growth. So we are really seeing true small cell deployment across the world, as well as massive MIMO type solutions coming up. So this is really happening this time. Okay, so one of the things that most people think when they see a graph like this is, okay, you're a device manufacturer. This usually means more dollars for you. You shouldn't be complaining about any of this at all. It should be true, but SWAP is a double-edged sword. It cuts both ways. You're trying to integrate so much stuff into a smaller form factor, a smaller system. It becomes really difficult for you to innovate and get to market faster by providing all that engineering in that short time frame. It's not really that easy. So we'll try to discuss this in a bit more detail in the coming slides. So digital pre-distortion is a necessary step in improving system efficiency. And what it enables you to do is use more nonlinear PAs. Nonlinear PAs imply higher efficiency PAs. So your system efficiency goes up because power amplifiers are notoriously the most inefficient block in a full RF signal chain. So if you can even squeeze out a few more percentage of efficiency out of it, you're golden. So DPD is just one of the ways that you can do it. You basically try to model the inverse of the PA and try to linearize the output of the PA by putting it in the signal chain. So you have a nonlinear PA now that you've linearized, basically giving you margin to spec, so your spurious emissions aren't that bad. You have a metric called ACLR, adjacent channel leakage ratio, that you want to push down. There's a 3 GBP spec for that. And you get better system efficiency. Sounds great. And this also means that your swap has now gone down. So it's a win-win-win, right? We'll talk about some of the trade-offs that are involved in DPD in a bit. But first, you must kind of understand, like, what are your different options. So you can go about modeling your PA as a simple polynomial. You can create a Wiener-Hammerstein or a GMP or generalized memory polynomial type of modeling solution, and you can start modeling your PA and create the inverse of it. One thing to understand here is that there's a difference between true RF, discrete, physical RF models of a PA versus a baseband approximation or a behavioral model of a PA. The baseband version is necessarily easier, a little bit more easier to learn, that is, as opposed to the RF model, which obviously requires a lot more degrees of freedom. So most DPD solutions end up being behavioral models just because it's more realizable. So what does it mean in the context of small cells for DPD? Small cells typically have the same spec requirement as macro base stations, but they also have additional constraints. So PoE, power over Ethernet, is considered as a power supply solution for small cells in most cases, so that drives some requirements. Passive cooling and integration obviously is a consideration. So if you took a macro base station type DPD solution and applied it to a small cell system, you end up getting an inefficient argument. So for a macro cell base station might have worked, but doesn't work for a small cell, right? Because now your PA efficiency improvement is kind of swamped over by just the DPD solution's power expenditure. So in an attempt to kind of make sure that people get the right kind of tools, we came out with integrated DPD as part of the 89375. This was released a few months ago. But here's an example of a real, like a small cell radio reference design. This is the kind of form factor that we're talking about. You're talking about something that is less than 10 centimeters square. And you want to be able to take this to market, and this is like a real solution, right? So like, for example, this box you see here, forget the green stuff. That's just a massively over-designed interposer board, just because we like it, like to do a lot of design here. But this is what you're talking about. This heat sink is just for cooling that small cell. So this is a real set of hardware that you can buy that could immediately go into a small cell, provided you can provide the baseband, right? Now, like I said, any discussion with DPD obviously needs a discussion on power amplifiers, so let's just jump right in. Talk about the state of the art for specifically with a comms focus. So you can see quite clearly here that LDMOS and GAS PAs are very prevalent in the industry as a de facto standard, depending on the frequency of operation, depending on the efficiency requirements and the output power level. So you do definitely see a lot of the LDMOS PAs in macro base stations and gas PAs in handsets, and as well as in infrastructure base stations. But in order to scale towards, let's say, sub-millimeter wave and millimeter wave type massive MIMO solutions, people are definitely looking at the benefits of GAN. So GAN imposes its own challenges, and that's what I'm trying to highlight here with the easily understandable, I hope, color-coded metrics here. So the process maturity isn't that great for GAN as compared to LDMOS PAs, and it typically has been only useful for saturated applications like radar, for example, not necessarily for comms. And they do impose a lot of memory effects challenges, and we'll talk more about what memory effects are in a bit. But first, I'd like to talk about the gain requirement for PAs and how that factors into your DPD solution. So a DPD solution is not just that one single P1 dB linearizer. Increasingly, PAs are sold in modules to customers, which means they have multiple gain stages, which means they have multiple gain expansion, compression artifacts. And what you see on the screen now is like an AM to AM curve. That's the blue curve you see here. Probably not pointing, am I? The blue curve that you see here is the AM to AM, which is your output distortion versus input power level, and the AM to PM, which is the phase modulation based on input power level. So you can see this is pretty nasty. Any DPD solution will struggle to kind of linearize this because you need a lot of degrees of freedom to be able to learn this model. And this is not the only model you have to go into learn. You have to learn different dynamic models as the power level switches, as the signal conditions vary. So it gets complicated really fast is what I'm trying to say. What you see in textbooks versus what happens in the real world, two different things. So moving on, what can you do as systems or an RF designer or whoever? What can you do to improve your DPD solution space? Let's say that this is what you're left with no tuning whatsoever. These PA modules are out there, and all you can get access to is this highly efficient PA, but it's practically useless because you can't linearize it. You can tune the biases of the PA that are available to you, because it used to be you could tweak the matching networks within the PA, or not within the PA, but between different gain stages to be able to extract some more efficiency or more linearity. But if you're only left with some bias knobs, then that's all you can play with. But you can do a lot with just that. That's what I'm trying to show here. This is a lot more ideal. It's just a much more benign looking AM to AM and AM to PM curve. And that's way more linearizable than this previous case. So I took an efficiency hit on the PA, maybe 2 to 5%, but I end up being able to use maybe an integrated DPD solution that gives me an overall system benefit. So we'll analyze that in a few more slides. Another thing to consider is memory effects. So think of memory effects as a non-instantaneous PA behavior. So let's say at time t equal to 0, your PA behaves as a sum of responses from the instantaneous envelope that it sees, the RF envelope that it sees at t equal to 0, but also in previous time. So this could be due to drain inductances, due to bias modulation, due to charge trapping effects, due to thermal management. It could be any number of things. And these are all just like a blanket term is memory effects. So key point here, this is usually encapsulated in a digital pre-distortion system as a delay term, right? And they cost computational resources. I'm going to skip this, but if there are questions, we can come back to this later. It's just a two-tone test that describes how to characterize memory effects. Another challenge with PA design is obviously pulsed waveforms. So even in LTE, you have conditions where you have sparse data. So you end up with a raw skeletal broadcast reference signal type of signal. And the frame, the subframe shown here, is the green symbols at the top. They're the data symbols. but the blue that you see here interspersed between are the reference signal symbols. In time domain, they end up looking like pulses. The reference signals start looking like pulses, which excites the PA in different ways depending on the process involved. So again, all of this pulsing changes the gain and the phase of the PA on a very short time frame. I'm talking the symbol time scale, so microseconds, right? So any DPD solution will struggle to characterize those kind of effects. So what you end up with, the very prominent effect that you see here is, let's say there's a 64 QAM data in this frame. You end up with a rotation in the PDSCH symbols, which really screws with your EVM, right? And think about 256 QAM or even 4096 if you're adventurous. Your EVM requirement, 3GPP spec for data EVM at 256 QAM is like 3.5%. You won't be able to hit that. And this is an intrinsic PA behavior that your DPD solution will be expected to correct. How do you, get past all of this? So just things for you to think about, right? Now that we are super familiar, that's your quick and dirty DPD plus PA lesson. What do we do with all of this information? Let's just go ahead and start designing a system, right? So easy. 2x2 small cell. Let's assume that your PA output power is 1 watt. That means 27 dBm at one antenna, 30 dBm total system power. 3 dB post-PA insertion loss is kind of forgiving. I'm just assuming that it's 3 dB. Let's just say poor design, whatever. 45 dBc, 3GPP target, 5 dB margin is kind of standard. At least you need that 5 dB. There might be other requirements that kind of play into this a little bit, so just be aware of it. Ideally, you don't want cost overruns, so cost per unit, $1,000. PoE plus specs, 25.5 watts for type 2 devices, so that's something for you to consider. We'd like to be within this power constraint, and just 2.6 gig pod for consideration here. And this is being designed as a small cell, but let's just add a quick twist to it and say, how about we take this design and scale it to a massive MIMO system? So let's explore that too. So in order to explore that, we need some sort of metric. So it's an easy enough number to come up with. Let's say this is your cost per unit and non-recurring expenses. So don your business hats and say CapEx and OpEx, and voila, you have some sort of metric, right? So assume like 2 years worth of product lifetime. That's a good figure of merit. There are multiple assumptions in this analysis, but the key point here is we are restricting our analysis to 3 main blocks, namely the FPGA or the baseband processing unit, the transceiver or the converter, and the PA, because these are the most power-hungry blocks in your signal chain, right? But that is not to take away from your power management, your clocks, your duplexer and filtering requirements, your spec compliance testing, which can take man hours, and lots of ATE tests and all that, all of non-recurring expenses, and also board area, layout costs, form factor, cooling. Those are all, they all figure into your total cost of operation in the end, but I'm kind of saying, okay, ignore that because we're focusing our attention on DPD. So case 0, this is not really a case because it's not really viable, mainly because it's a backed off PA. A backed off PA is necessary because in OFDM with a higher PAR, you end up having to back off the PA if you don't want to run into saturation, right? So if you want usable data. So this is not really viable, and there are definitely some heat sinking constraints that you can imagine here. So there are 2 different ways to do this. Let's say you do want to do some observation or not. I'm going to choose this particular implementation, which is 8 SerDes lanes for 1 transceiver, just 2 TX and 1 FPGA. So the more conventional DPD solution would be you design your own DPD IP, implement it in ASIC or in the FPGA, or you rely on the vendor to provide you some DPD IP. And lots of FPGA vendors do this now, and you can buy it. You can buy the whole solution, if you will. This improves your PA efficiency from, let's say, it was 10% to 35%. It's a huge increase, right? Which is what this is all about. This is all about efficiency. This is all about a numbers game. And this is definitely scalable, but it does cost more because you have to pay more for IP. You get a more power hungry, more faster FPGA, and you end up spending a lot more than you would with the backed off PA if you don't do it right. What other options do we have? So like I mentioned earlier, you could integrate DPD into a non-FPGA block. And that's what we are proposing here. So traditionally, like ADI's transceivers, the ones that you're familiar with, the 9361 and its family of products, they've moved a lot of the signal processing into the transceiver. So the AGC and the IQ imbalance corrections and so on have been in the transceiver for the last 7 years. But with this 9375, you move even the DPD block into the transceiver, right? So can you just do DPD? Actually, no, because you end up taking on the responsibility for managing the PA. So you say that you want to do closed loop gain control, you want to do VisWAR measurements, you want to do PA bias control, a whole bunch of other things that you're signing up for. So that enables you to lower your overhead, system overhead, by taking what used to be done traditionally in an FPGA, reduce the number of lanes that the FPGA needs to talk to the transceiver, and we'll get to that in a bit, and also run the calibrations closer to the source. So the 9375 is just 7.1 with DPD. So 7 was introduced last year. So this is just an example here how you could take the 7.5 and reduce your TX lane rate, completely do away with your ORX or your observation receive, because you don't want to do any DPD or PA management functions in your baseband or in your FPGA. So that saves you a lot of power, interface power, as well as FPGA complexity, right? So maybe now you can choose a cheaper FPGA, lower speed grade, whatever. So in this case, this is what I'm saying here, same efficiency improvement. Let's say this is 40 megahertz bandwidth, we can still do it. Maybe a lower speed grade part, and use the 7.5, you're down to 4 SerDes lanes. What does this all mean, and how can you visualize this? So this is an interesting way to look at it. So if I scaled a 2T2R system into a 32T, a 32 by 32 or 64 by 64 system, how much improvement can I get from using all these different types of architectures? And the numbers show, and these are all like based on what I could find on DigiKey or Xilinx and ADI websites for 1,000+ units. So you could see that the integrated DPD solution offers you quite more improvement in the figure of merit that I just established over a lifetime as you increase the number of signal chains. So that makes it a compelling argument to start looking at it as a architectural alternative. So you can see that probably you can see, even I can't see it. It's the integrated DPD is like $850 over 2 years total, whereas the backed off solution is $966 and FPGA is like $962. These are still estimates, but good estimates based on whatever I could find on the internet. So in conclusion, what does this mean? It means system complexity, for sure. There's increasing DPD complexity. There are challenges imposed by your PA. This all ties it back to increasing system complexity. GAN is coming. It's inevitable, something that we all have to worry about. Some people celebrate, some people worry. There's also an evolving business model in the comms industry where there's more co-development between different vendors. And this means there's more of a hardware design trade-off in the system, right? So Scalability plays a part in any systems design, so that's still true. You still want faster time to market, lower BOM cost. And now this is where it gets interesting, where you say, okay, so it's not the DPD solution which has the best ACLR, it's not the one which has the best EVM, it's kind of a mix of all of this, because as I was trying to show, maybe the FPGA DPD has better ACLR metrics, better EVM, but you lose on 2 years worth of operating expenditure. Can you save that much money by choosing a different architecture? It's worth considering, right? So that's what I want you to take away from this presentation. Just think about these kind of system-level problems. So what can the GNU Radio community do to enable systems design? One of the main problems that I see is there's no full signal chain algorithm development sort of emphasis given, at least in things that I could readily read. So if someone knows of activities or projects, let me know. Maybe one of the solutions that you could do is like use reference designs that are readily available from different vendors, ADI, Xilinx, whoever, and try to use these systems because they're more representative of a real-world system than anything you can probably find, right? Lack of LTE support is a bit concerning, and there are definitely some signal analysis that you could be doing with GNU Radio that I would like to get away from some of the proprietary tools and software. And not everything is software defined, not just yet, right? So hardware design trade-offs will help you get better results when it is available. There are times when you can do software fixes to a lot of things, but in the end, if you can fix something in hardware, make your system better overall by hardware trade-offs, use it, and then make your software a little bit simpler, less complex. So just a few things to think about, right? With that said, I'd like to thank you, and Q&A. And
all right, thank you. Do we have any questions? What's up, Marcus? You need a mic.
He's pretty loud.
Behind you.
He's usually pretty loud.
Yeah, that's true.
So I like the whole angle of what can the GNU Radio community take from that. So is there some reference software simulator or implementation from ADA, maybe even, that one could adapt? I mean, GNU Radio does have some hardware impairments models that come with the standard installation. But of course, these are relatively simple compared to like seeing a time variant, nonlinear, band-dependent kind of thing. So is there some things that are not only literature, read and implement your own, but also like pre-made tests, but like reference that I can actually test my own hardware simulator against?
Yeah, I'll probably defer to Robin on that one, but I'm pretty sure there's like IO device models that we support for 7.1 and 7.5. The main challenge is the data throughput and how you handle all this data. You're talking like 61 megasamples per second.
Obviously, but in simulation, that already would allow me to understand my whole system as I apply it to, for example, simulated LTE.
Right.
So, yeah.
Okay. Yeah, that's a valid point. I mean, if you want to come back to us during the booth, we can talk about it a lot more. But Robin, do you have anything here as a hot? The only, sorry?
The only simulation models of LTE that I'm familiar with are commercial models.
So just for anyone who didn't hear it, Robin was saying that the only simulation options that he's aware of for commercial LTE, or sorry, the only simulation options that he's aware of for LTE are commercial. And by commercial, I assume you mean not commercial open source, but commercial proprietary? Yeah. Any other questions? Nope. All right. Let's thank our speaker. Thank you so much.
All right. Thank you.
All right. So while we get situated for the panel, Michelle is going to come up and give us a quick update on the hacking challenge.
And also, we have 2 lost and found items, a little recorder found a recorder out on the registration area, so check and make sure if you have a little recorder. If it's missing, I probably have it. And also, if you spoke this morning and you had what looks like a Surface Pro, the Surface Pro charger was left up here at the podium, and I have that, so come check with me if either one of these things is missing. All right, so we have 37 teams registered. 30 of those teams are on the board. GRCon17 is in the lead. Mossman and Popats are tied for second, and then Adversarial Science Lab is in third. So I've given some completely facetious awards here because I can. So Adversarial Science Lab has earned the Cool Name Award, and it's plus 25 points. And we have a team called Megahertz, so I made up a technical pun award and gave it to them. And the Unconfined _ gets the Bug Hunt Award. They were leading with a whopping like 1,200 points, but that's because I left some of the keys blank, and all you had to do was hit return. Right. So I made up for that 1,200 points that I took away by giving them 200. All right, so I have a Black Ribbon Award, and that is the OATK team, which is probably Orbital ATK. And that's a real company. Some of you probably have heard of Orbital ATK, right? So they were in last place, so I gave them 11 points so that they would beat the fictional company name Wayland, the team Wayland, which is from Alien. So I had to have a real company beat out the fake one. Anyway, that's the update for the game. If you have any questions or you don't know where to start or you're confused by a challenge, please come talk to me and I'll help you out. We're here to learn, and if it's confusing or if the key doesn't seem to work, just come bug me. And again, if you have an idea for a challenge or a prank or a puzzle, we'll put it in there. We'll figure out a points award, and you get the points right off the bat, and maybe a bonus for contributing. All right.
Awesome. Thank you, Michelle. Okay, so we're going to go ahead and get the panel going, which means I need my moderator, Mr. Tim Newman. And we also need the other panelists. Has anyone seen Jonathan Corgan or Martin Baran?